Check out dynamic programming problem right here. Dynamic programming is one of those concepts which freaks people out. They say, how can I ever solve a DP problem, a dynamic programming challenge? In all likelihood, you're just not likely to get one of these questions in an interview. Maybe if you're at Google or Facebook or some FANG company or just some company full of jerks that wants to really screw you with a terrible question because they don't like you. Maybe they'll give you one of these questions. Anyway, you can totally solve these. There's a few patterns, concepts that we're going to go over in this video. I'm going to try to solve a DP problem in real time. And I'll tell you, I've solved this problem before. It's very similar to a lot of DP type problems you're going to solve. And when you read it, it sounds really complicated. We're going to see exactly how you go about it and how it's actually really simple way to actually solve problems that otherwise might use a ton of recursion, create a ton of calls on the call stack, and otherwise not be very performant. Anyway, this one's called unique paths. I'm not going to read it. You can read it yourself, really, but it's about a little robot. And it says, hey, how can this robot get down here to the finish line? How many different unique paths can a robot take? In this case, we have m equals 3. So we have at the top row is 3, and at the bottom is 7. Actually, I did this completely wrong. It's should have been 3. Should have been 3 going down and 7 across. Anyway, that's okay. This will be the same answer either way. Doesn't really matter. So he's always going to start in the top left corner. He's always going to move to the bottom right corner. That is the constraint of this problem. Top right to the top left to the bottom right corner. And we need to find all the unique ways he can get to there. So in a problem like this, I like to kind of draw it out. So I have like this little matrix here. And I have the input M3, N7, and the output is going to be 28. And we're actually going to make this, why don't we actually make this look the actual way the problem should. That way there's no confusion or you think, wait a second, that's not how I interpreted the problem. So we have 1, 2, 3 rows here, and we're going to erase these other ones for the sake of just being very clear and sticking to the problem. So first of all, how many ways can you get? Let's pretend this grid was really, really small. What if this was a grid of just one? So the idea of dynamic programming is to build up an answer based on previous answers. So it means that if you know an answer to a subproblem, you can use that subproblem to then answer another subproblem. You can answer that next subproblem to answer another subproblem until you get to the very final item in your problem list or whatever, your the thing you're trying to solve. You take all your previous answers and you use them to get to your final conclusion. Now, in practice, what does that look like? Let's say for unique paths, let's say we only had a table, we only had M1 and N1. We had a table. How many unique paths are in here? Well, there's only one, right? What if we added a row, added a space in there? How many ways can you get to the next one? One, right? In fact, if this was a straight line, well, we know there's only one way to get to it. Literally, you can't go down or anything. You can only go across in a straight line. So there's only one way to get to this square. There's only one way to get to this square. And there's only one way to get to this square. What if we had it like this? How many ways can you get down to this one? Well, there's only one way. The only way is going down. Now, what about this one? This is interesting. Well, there's one way to get to here, and there's one way to get to here. And let's see, you can go to the right and you can go down, or you can go down and you can go to the right. So what does that mean? There's two ways. Interesting. Let's see if we can find a pattern here. There's only one way to get here. We've already established that. There's only one way to get to any space in the very uppermost row, right? You can only go across. You can only go to the right, right? And the same thing with going down. So what about this space right here? Let's see. You could go to the right. You can go down. You can go across. That's one way. You could go to the right again, and go down. That's two ways. Or you can go down to the right and to the right. That's three ways. Remember, you can only go down or right at any given time. That's one of the other constraints of this problem. There's three ways. Do you see the pattern yet? If you add the number of ways to get to this space and the number of ways to get to this space, well, then you have the number of ways to get to this space, right? And you can start off with saying every single item in the top row is only have one way to get to it. Every single item going vertically in that leftmost row only has one way to get to that. Everything else is going to be the addition of the row of the space directly above and the space directly to the left. makes sense, right? Because if there's two ways to get here and there's one way to get here, well, we know that the way to get to the next row is obviously if there's two ways to get to the row right next to me and the only one to get to the row right above me, that means there's one way to get to the row right above me and two ways to get to the row right next to me. That means there are a total of three ways to get to where I am right there. And that makes some common sense, right? So we take this pattern that we've established here by looking at really small problems. Remember, we started off with a pretty small problem. And you're going to see this a lot in dynamic programming problems. The pattern of using arrays to group subproblems. So Fibonacci is another way you can do this. I definitely suggest you look at some other DP problems, and then you realize that these typically involve an array. You already kind of need to know a few of the initial answers. So once you can establish that okay, well if I only have this many inputs, I know the answer is this. And once you can get that, like I said, well, if I have one, you just go smaller and smaller and smaller until you get that initial answer, and then you build up off that initial answer. And sometimes you look for patterns, and it's a little bit of intuition on how to do this, but this is a very common, typical way to solve this kind of problem. So let's go with this real quick. We're going to kind of fly through this one. So we know that there's one way to get here. We know 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 there's one way to get here, and there's one way to get here, and there's one way to get here. Right? Same thing here, 1 and 1. So now we start doing our problem solving. We say 1 and 1 is 2. 1 and 2 ways to get here is 3. There is 1 plus 3 ways to get here, which is 4. There is 1 plus 4 ways to get here is 5. And there is 1 plus 5 ways to get here, which is 6. And there is 1 plus 6 ways to get here, which is 7. So let's see now what this yields here. We have 3 ways to get here, which means there are 6 ways to get here, which means there are 10 ways to get here, which means there are 15 freaking ways to get here. And lastly, we have 21 ways to get here. And guess what the last one is? 28. What is our output? 28. If it seems overly simple, maybe because it is. Now let's actually try to write some code for this. So we're going to iterate over m and n. So let's do for let I equals 0 such that I is less than m, I plus plus, and then we're going to iterate over. This is a matrix, right? So we have two for loops. For let j equals 0 such that j is less than n. Do j plus plus. Now here's the part where we let's initialize leftmost row and top leftmost column, right? Leftmost column and topmost row set to 1, right? So let's see, how do we determine that? So we look first of all, if the row, so this would be in this case 0 0 0 1 0 2. Okay, so we know that if I is 0, if I equals 0, or so we have, so this one, so we have what in this row we have 0 1, we have 0 at index 2, and we have 0 at 3. Remember, this is a matrix, right? And then we have going down, we have 1 1 0 2 0. So basically, if I equals 0 or what's it called, j equals 0, then we're going to then what's it called, then oh yeah, what do we want to do here? So we want to let's actually, so we need to probably make a matrix, right? We're going to make a matrix with so many rows and stuff. So we're going to call this matrix equals this. And then let's start pushing in some items. We basically want to make this matrix and then fill it in with some stuff so we can begin filling it in and doing our problem solving. Matrix dot push an empty array, and then we'll do this if I equals 0 or j equals 0, the matrix at I j equals 1, or we'll set it to 1. Now what I like to do is just to make sure I'm actually doing things correctly. Let's just console.log our matrix and see what we get here. in the code. Oops. Okay. So we need to do that. So let's go back out. We'll take that. We'll add that. Else matrix I j else matrix ij equals matrix I minus 1. So we look at the row right above us. Matrix I minus 1 j plus matrix I, and then we'll look at the one to the left of us to be j minus 1. So let's see what our matrix looks like now. And look at that. Now, at this point, so this seems actually kind of overly simple, right? So now all we need to really do is take the very last item in the matrix. So now we take matrix. Let's see. Let's get the length of the matrix. Actually, I think we just need to get matrix at m minus 1, n minus 1. So m minus 1, n minus 1. Let's see if that works. Let's just return it. And there we go. So that's literally it. Why is it n minus 1, n minus 1? That's because obviously arrays are 0 indexed. Well, not obviously. Maybe if you're watching this, I hope you understand how arrays work. But that's actually about as simple as you can do. This is a DP problem. It's actually a median problem, unique path. Now, a lot of the time was actually spent building up our case and understanding exactly what we were doing here. The actual code implementation wasn't really that difficult. We started off with a matrix. We went, we go row by row. We push in an empty array for that row. We look if we're either at the leftmost column or the topmost row, and we just say, well, that we know that there's only one way to get to those spots, right? That we've established that already. And in the other case that it's not in that leftmost or topmost area, then we know it's simply the sum of the number of ways you got to the cell directly above you plus the number of ways you got to the cell directly to the left of you. And you add those ways, and we kind of established why that's the case here. I don't know if this code will submit and work, but let's see. It did pretty good. Decent memory usage, whatever. But we actually solved it. Definitely challenge you to go do some of these on your own and check them out. And hopefully you got something out of that. And you realize that DP problems really aren't that scary, but you probably won't see these too much in a while. They are kind of a parlor trick.